In this recording, we will discuss how fields are going to add up and how would that impact fields and distribution of charges in conductors and insulators as well. Okay, now this is from a particular simulation that I have the URL to in the next slide. But what we start here is with three charges. One charge in the middle, and then two charges, one 10 degrees above and one 10 degrees below. Now the overall electrical field at this point here is going to be the electrical field due to the top charge. That's going to be like this. Due to the bottom charge, that's going to be like this. All are positive charges. Due to the middle, that's going to be like this. Overall, they add up to what is shown in blue. Since the angles are the same up and down, the vertical components of the electrical field are going to cancel out, and the horizontal components will add up to have a result of 30 newtons per coulomb in this case. And actually, the unit is arbitrary. I just put newtons per coulomb to 0.30, whatever. Okay, now if we add more, for example, here we added two more on top and two more on the bottom. Of course, the vertical components, because of the symmetry, are going to continue to cancel, but the horizontal component is going to increase, and we have a stronger electrical field. It keeps on increasing here when I added even more charges in both sides. It keeps on increasing. Essentially here I have almost half a circle. Okay, and I have a larger electrical field along the horizontal. Now, what if I keep on adding? Now, what's going to happen is these charges now are going to have an electrical field pointing in the opposite direction. What's that going to do? It's going to diminish that horizontal component because, again, they cancel out vertically, but that horizontal component is going to be in the negative direction. So instead of having 1.14, you see here we have 1.04 newtons per coulomb. And as I keep adding charges along the circle, that horizontal component of the electrical field is starting to diminish, getting even smaller. So when I have a full circle, then what you need to remember is half the circle is producing an electrical field in this direction. The other half is producing an equal electrical field in the opposite direction, such that the overall electrical field is going to be zero. You can check the simulation at that website if you want to. Now, this is another simulation doing the same thing. Okay. So we start, but actually with many more charges. But we start with some charge here, and as the charge number increases, you see here the electrical field all the way around. Now, the electrical field here due to half a circle, you see it here, it's quite straight. You see the orientation here. And that's the electrical field due to the all charges. And when the circle starts closing up, see it here, then the electrical field in the middle is going to diminish. When it is fully closed, this is the interesting thing, there is no more electrical field inside. Okay. Now the contribution of each of the charges is being cancelled out due to the other charges. This has some quite interesting implications. Okay, before getting to those implications, let's discuss something else too. What we call a uniform electrical field. What if I have a region where I have a constant electrical field? That's what we define as uniform electrical field. Now, then the electrical field is going to look the same throughout that region, like what we have here. Now, if I place a charge in that uniform electrical field, If the charge is tiny, it's not going to affect the electrical field, but it's going to experience a force. That force is going to be given, like we said before, Q times E. Now, if our charge is tiny, again, a test charge, so it will not affect the electrical field, the force is QE, and the force is going to be in the same direction as the electrical field if the charge is positive. It's going to be in the opposite direction if I have a negative charge. Okay, this is a positive charge, that's a negative charge. This is just an illustration. What if I have a big charge, a large charge that I add to a region of uniform electrical field? Of course, if I'm going to add a large charge, that's going to affect the uniform electrical field, and it's not uniform anymore. Like in this case, we don't have a uniform electrical field anymore. Okay, now let's take the case of a conductor. Okay, and I have a simulation that I set up for that, and let's put some charges in the conductor. What's going to happen to the charges? They are going to repel each other. Okay, what does that mean if they repel each other? They are going to try to move as far away from each other as they can. Each charge is exerting forces on the other charges, and it's going to experience forces due to the other charges. So what's going to happen is they are going to try to spread out as far away as possible within the conductor from themselves. Where's that as far away as possible going to be? It's going to be at the surface of the conductor, like we see here. Now with small anomalies like you see here in the corners. Okay, now what does that mean? Think of a charge here. What is it going to experience? It's going to experience of a repulsive force from a charge here. That force is going to be like this. It's going to experience a force from this one. That's going to be like this. It's going to experience a force from this one. That's going to be like this. It's going to experience a force from this one. That's going to be like this. It's going to experience a force from this one. That's going to be like this. So the overall net force acting on that charge is going to pin it to that particular location of the surface. There is no force pulling it inwards, and that's why it's going to stay at the surface. Now, corners are a little bit more complicated, and we'll get to them in a second, in a little bit. Now, what about the electrical field surrounding the conductor? So now I have charges all throughout. What would be the electrical field around the conductor? Now the electrical field is going to be the electrical field, the sum of the electrical fields due to all the charges. And we see a configuration that shows us somewhat that. Now, if this were an insulator instead, the charges are not going to be able to be displaced towards the surface. Actually, I need to mention a point there that I almost forgot to mention. Now, the charges are going to be all around the surface here in the conductor, but like the case that we talked about here, the electrical fields inside are going to add up to give us an electrical field equal to 0 inside. So the charges are going to distribute themselves in a way that the electrical field inside the conductor is going to be 0. Now, however, for an insulator, since the charges are going to be stuck inside, the electrical field is not going to be 0 inside. Now, another thing worth noting, what if I have a spherical symmetry? If I have a spherical symmetry, it's the same case that we just talked about with the charges all the way around the center. So I should have an electrical field equal to 0 here. The electrical field at the surface is perpendicular to the circle. Now, for a conductor here that's not spherical in shape, you notice a couple of screens back, the electrical field has some kind of a complicated pattern here. However, when you get very close to the surface, the electrical field is going to be perpendicular to the surface. So the charges are going to distribute themselves such that the electrical field is perpendicular to the surface of a conductor. That's throughout the conductor. It does not matter if it is a sharp edge or whatever. That's not going to be the case for an insulator. Now, if you go, for example, to this simulation and move the charges nearby, you'll see as you move them close to wherever, the force acting on them is going to be perpendicular to the surface. Now, again, to explain what's happening in a conductor, if I have a spherical symmetry like this, now all the forces are going to be such that the only force felt by a charge is going to be perpendicular to the surface, pushing the charge away or towards the outside of the conductor while being stuck in the conductor. And we'll have a uniform distribution of charges. However, if we don't have that spherical symmetry, if we have something like this, like a strip, now you notice the charge in the middle is going to feel equal number of charges, so the force acting on it is 0. However, this charge is going to feel more forces from this side than from this side. So it's going to experience a net force towards the right. This charge is going to feel even more charges from this side than this side. So it's going to feel a net force in this direction, towards the right again. So what's the net effect of that? The net effect of that is I'm going to have charges piling up at both ends, instead of being spread out evenly, like in the case of spherical symmetry. Actually, this is misplaced. Let me jump here first. That's why, actually, charges are going to accumulate during sharper edges. Another thing that you might think of in a sharp edge like this, a charge from here, it's going to feel the forces due to the other charges, but it's the force that it's going to feel from these charges here is trying to pin it there, and here it's trying to pin it here. So it's trying to keep it stuck in that corner. And that's why in the cases of conductors, we are going to have more charges accumulate at sharper edges than on flat surfaces. Another interesting thing about conductors. Let's take this case here. What if I have a negative charge and I place it in the middle of a hollow sphere, a hollow conducting sphere? Okay, what's going to happen? Okay, let's forget about this for a second. What's going to happen? That negative charge here in the middle is going to repel the negative charges that are in the metal. Where is it going to repel them? Those negative charges are going to go to the outer surface. So as a consequence, we are going to have a net positive charge in the inner surface, but a net negative charge in the outer surface. Okay. And because of charge balance, the negative charge in the outer surface is going to be the same as the negative charge in the middle of the sphere. Now let's go back to our case here, our question here. What if I place a positive charge near it? what's going to happen if I place a positive charge? The positive charge is going to attract negative charges towards this end. And leaving a net positive charge on the opposite end. But you notice here the difference. This is a little bit thicker than this. Why is it thicker? Because of that negative charge inside. That, what we talked about a second ago, resulted in a net negative charge in the outer surface. So that negative charge is going to come towards this end. However, what's interesting, this charge is being shielded from this charge. So it's not going to be affected by any force from this charge. What's going to be affected are the charges along the surface. Now, in summary, in conductors, electrons are free to move. They are going to feel the electrical force. They will move until they reach static equilibrium where there is no more force. That static equilibrium happens when we obtain an electrical field equal to 0. Which brings us to this. That's very important. The electrical field inside a conductor is always 0 under static conditions. Now, excess charge on an isolated conductor, whenever we add charges on an isolated conductor, they will reside entirely on the surface. Another thing that's important, just outside the conductor, the electrical field is perpendicular to the surface. Just outside, the minute you go further away from the surface, it becomes more complicated. Now, on irregularly shaped conductors, charges accumulate at sharper ends. We have a bigger charge buildup at the sharp